Hello, this is going to be a breakdown on how I've put together a start pathfinding to create a simple roguelike turn-based game if I just run the game. So first things first, I can move around with the arrow keys, and if I click I can create a path and walk along that path. If I click through this house, I will move through the inside and come out the back whilst avoiding any walls and props, so I can't click on a table or a chair, I just won't move there. Every time the player moves, you can see these zombies are making their way towards the player, and they utilize the same path system so they can do the same things the player can, and at the moment their aim is just to get in your way. If a zombie walks into your path, then the player will just stop and you have to make another decision again. Before diving into any code, I want to begin by explaining my scene structure. So over here I have two tile maps. The path tile map is the one with the A-star grid on it, and it will synchronize all the tiles with that grid. So any tile on this tile map will act as a blocking object basically. On the non-blocking tile map, if I view it, then we can view the doors. These aren't registered with the A-star grid, so they have no impact on the pathfinding. Under the path tile map is a line 2D. This I use for displaying the player's path, and then we have a player and two zombie nodes. Alright, so let's get into some code. If I click on the path tile map and click on the script, here's my script which is extending a tile map, and I've got a variable for A-star on ready. I initialize A-star as a new A-star 2D instance, and then I generate the grid. The generate grid function starts by clearing down the grid, only because we might call this function multiple times, and then I get the used area of the tile map and assign that to a variable called size. Now this is only just done for convenience, so I don't repeatedly have to call getUseRec.size. Next, I reserve the space on the A-star grid, which is a count of all tiles that we have in our grid. So this loop here is looping through every cell in the tile map, regardless of if there's a tile there or not. And we take the X and Y and convert it to a vector 2, and then that vector 2 can get passed into these two functions. So map to world is taking the tile position and multiplying it by the cell size. In my case that's 8 by 8. And the get tile ID is just taking the X and Y and calculating the ID of that tile in the sequence. So for A-star.addPoint, this is creating a cell in the A-star grid, and it takes the tile ID and it takes a position, and then it takes this value at the end. So this is the weight of that tile. A higher weight means the tile is more difficult to pass, and a lower weight is more easier, and A-star will try and calculate the easiest path to take. As this is just a simple turn-based roguelike game, then it doesn't really need complex pathfinding, so all the tiles are the same weight, they're 1. The loop below is similar to the one above, where I'm looping through every cell in the tile map. I get the tile ID from that position, and then referring to that point on the A-star grid, I check if there are any adjacent points that exist. If they exist, then I connect those points together. Basically, any points that are connected indicate a valid path between those 2 points. And you see I've got the cardinal directions here, so that means you can move up, down, left and right. If you wanted to allow for diagonal movement, then you'd have to check against the top left, top right, bottom left and bottom right as well. At the bottom where I'm checking get cell, I'm basically checking that the current cell has a tile. If it has a tile, then the point on the A-star grid gets disabled. This is so that no path can be generated through that cell, and no entity can enter that cell either. Once the grid is generated, I emit a signal saying grid refreshed. Now there's one function I did not cover, and that's the get tile ID, which accepts a tile position. I deduct the get used rect.position from the tile position to get a position that always begins at 0, 0. And then I compute an ID from that position by taking the X value and adding it together to the Y value multiplied by the width of the tile map. Moving down to the functions below, free cell and reserve cell both take a world position. That world position is then converted to a map position, which can be used to get the tile ID, and then referencing the A star grid, checking if that point exists, and then changing the disabled status of that point. Can move to takes a world position again, converts that to a map position and gets the tile ID. It gets referenced to the A star grid, checks if that point exists, and also checks that that point is not disabled. Get move path is the function that builds a path from the current world position to a target world position. It does again similar to what's been going on before, converting the positions to the map position and get the tile ID. And then in A star we check these points exist, and then we return a path between those 2 points as an array. And here I've got a signal, well, I'm catching a signal for the on player moved signal, and I check all the children under this node. If they have the method move towards player, then they're told to move towards the player. This is just my cheap implementation of enemy AI at the moment. Okay, that's it for the grid manager. Next up is the player script. As you see, I've got a var for the move path, and I've got an unready var for the grid manager and the cell size, and also a reference to the path for this line 2D node here. For the cell size, I'm pretty much just picking this from the grid manager, the path tile map, cell size here 8x8. Coming down a bit on my process method, I'm checking against any input actions. So any like moving up, down, left and right is taking the cell size and either adding it or subtracting it against the corresponding axes. Next is the touch or the mouse click action. When the mouse is clicked, I get the mouse position from the camera 2D, and then I subtract half of the cell size, which just makes sure the mouse position is nice and centered on the tile. The points come from the grid manager, calling the get move path function. I pass in the player's position and the mouse position snapped to the cell size, and that will give us an array of points back. If the size of the points array is greater than 1, then the points get assigned to the move path, and the first item in the move path gets popped off the array. This is because the first item is the current position of the player, so it makes no sense in keeping that bit. The sleep timer is fired, and when that times out, it just moves the player through the array of positions that we set. So if the move path size is greater than 0, meaning we have positions to still go through, then we pop off the front of the array again. We assign it to the move to variable, and then we check that that position isn't the same position. We ask the grid manager if we can move to that position. If so, we move, and then we start the sleep timer again, which repeats this process until there are no more items in the array to move through. Lastly, we have the zombie or the enemy script to have a look at. Similar thing happens here. We get the grid manager from the parent. We've got a moved signal. We connect to the grid manager. We listen to when the grid is refreshed or the first time it's built, and then we call the sync with grid function. The sync with grid function just takes the current enemy position and reserves that cell. This is necessary because you don't want zombies or any enemy in particular from being able to occupy another enemy cell. For the move towards player method, we have to free the current cell the enemy is sat on, otherwise we won't be able to calculate a path from the position to the target position. And then at the end of the process, we reserve that cell again. So if the enemy moves or not, it'll either free the last position and then reserve the current position, or it'll just free the current position and reserve the current position again. Between this process, I call the getMovePath from the grid manager again. I pass in the current position and the player's position as the target position. And if the move path size is greater than 2 this time, this is because we want to exclude our current position and we want to exclude the player's end position. We only want to focus on the path in between those two. So that's why it's greater than 2 instead of 1 this time. And then for the move path, we do the same again and just remove the first record because we don't want to move to our current position. And then we just take the follow-on position from that, which is the adjacent cell from where we're moving to, and we move to that position. We don't need to check if that position is available because we've just generated a path from it, so we know that at least the adjacent cell is available. And that is how the enemy AI moves. It's pretty simplistic. There's no logic involved, and when they get to the player, they don't really do anything else from that point on. Alright, that's all. I've included a link to the project below. If you'd like to experiment or use this project as a starting point, then you are free to do so. No credit is necessary, just make sure to credit kenny.nl for the assets used. Thanks for watching.